Okay. So so today, after a week of a break, we continue with what we were talking about last time. And just to recap, we talked about Pickering stabilization, how particles could stick to soft interfaces, and we looked at the continuous model for that. So we looked at Pieranski, and just by playing with interfacial tangents and interfacial energies, we could argue why particles would stick, and we could also argue why larger particles would not stick as a result of surface roughness. So today we're going to shrink the system a bit. I'm going to look at what happens now if particles become really small. And then because in lectures 2, 3, and 4, we talked about mini-emulsion polymerization and emulsion polymerization. So the concept then is, what if we integrate these two, combine these two things together? What do we end up with then, and what can we make then? So that's hopefully what we're going to do today. So hopefully you remember a little bit about emulsion and mini-emulsion polymerization, and then you can understand how this works. So okay, so if I'm correct, this is where we stopped last time. We had a particle stuck at a liquid-liquid interface, and we came up with this big expression that basically the only thing that was there was the energy between the particle in phase 1, the energy in the particle phase 2, and the energy you take away by placing a particle at the liquid-liquid interface. And we divided that by thermal energy to get a dimensionless energy that kind of gives an idea on how strong this interaction is with respect to thermal energy. And that yielded us this, the first big term. So it scales with r to the power 2. And then you got this large expression that was a quadratic expression as a function of the relative height that the particle sat at the liquid-liquid interface. Now that equation works pretty well for large systems. However, we ignored a few things. So one thing we ignored is that in this 2D picture, there are 2 points at which you can identify that 3 phases are in contact with each other. So let's point to the left here and point to the right there. So that is a little bit something bizarre. So if 2 phases are in contact with each other, we talk about interfacial energy, and it scales with an area. So if 3 phases are in contact with each other, effectively you can draw a circle around a spherical particle that 3 phases are in contact with each other. So that could be a one-dimensional equivalent of interfacial tension, which in literature is often referred to as line tension. So line tension is this extra term that's been added here with symbol tau in that particular case. And so you see that scales with, the circumference basically of a circle in this case. And it obviously depends on, again, of z, because depending on where this position lies. So 50-50 is when z is basically 0. So then it's the larger. So it's a correction term almost. Now the tricky bit is line tension is a bit of a controversy, and it's very difficult to measure. So there are no numbers for this really. There are a few numbers in literature, but and the reason why it's more complicated is that there are a few other things that start to play a role if you shrink this particle. And one of the things is that a liquid-liquid or liquid-air interface, through its thermal motion, will not be flat. Right? I've drawn here just a straight line, but obviously these things can move. So maybe it's a little bit more like the ocean or the sea, and you get a wave over it as a result of this random motion. So that is called, that wave is called the capillary wave. And then another thing which is important, like if my particle becomes really small, say like 1-2 nanometer, my molecules are almost of the same order of magnitude. So like a water molecule is, it's smaller than a nanometer, but it'll be about, 0.1 to 0.2 nanometer. So you almost have like tiny little ping pong balls bumping into a slightly larger ping pong ball, which means that continuous wetting starts to become a little bit vague. Yeah? So you have like a bit more like discrete wetting rather than continuous wetting. So those terms kind of make this understanding of line tension a little bit diffuse. So how could you address this? Well, this is, one thing where simulations can come in very useful. So David Chung at Warwick I don't know whether you guys know. You guys must know him, right? The theory guy. He's pretty good. And myself, we looked at this problem. So at the top picture here, you see a liquid-liquid interface. And you can clearly see already that this interface is not flat. You see it, the picture on the top left, you see there's a bit of a wobble over it. And that wavy pattern is your capillary wave. Now, you also see that in a liquid and a liquid, there's always a little bit of one liquid dissolving in the other liquid. Yeah? So that's logical. It's just thermodynamics, right? So if you have a liquid-liquid interface, if this would be oil and water, there's always a little bit of water in the oil phase, and there's always a little bit of oil in the water phase. It's saturated, both phases. So then the question is, what if I just put a particle in the middle? So, and in this particular case, the particle is blue, but that doesn't really matter. And it's slightly larger, so we can vary the size of the particle. So in picture C, the particle is slightly bigger than in picture B. And then we just look at how this particle behaves. So we track how it moves, and as a result of that, we can calculate the free energy of that particle. Does it stick? Where roughly does it sit? And then you get, if you do that, you get a similar graph as we've seen before. So what do I have to say is that the blue particle likes the green phase just as much as it likes the gray phase. So it's symmetrical, yeah? Which means that if it would be symmetrical, it would sit exactly in the middle if it would be a Pieranski system. So there's no difference between the tensions between blue and green and blue and gray. So in the top image here, you see the distance divided by the size of the particle, and in the y-axis you see the free energy effectively. And so let's just focus at the blue lines, right? So the blue dotted line is the Pieranski model. So the continuous model, of which we talked about before, and you see just, half of a parabolic expression, and it just flattens out, and that's the well. Now what you see here, that if you do the simulation, which is the continuous line, the continuous curve, you'll see that A, the well is deeper, and B, the well is wider. So wider, you could argue, maybe if this wavy pattern is over there, it can kind of grab the particle sometimes from a larger distance and pull it in. So that's why, so the capillary wave causes this line to be slightly wider. And then the depth of the well, you could argue, well, that is this line tension thing and this discrete wetting thing that comes on top of it. And if you would plot that deviation, so if you would plot free energy divided by free energy Pieranski, you could kind of see, or you could argue that there is a linear, well, roughly linear, correction term on this, which corresponds to a line tension term. So the overall qualitative message of this is, if stuff becomes really small, continuous modeling becomes an issue, and you have to look at a more complex case. And what people do is they add this line tension term to it in order to, you could almost say maybe it's just a fitting parameter, yeah. But overall message is, small stuff sticks better than we would predict, even with up to 50% deviation in some cases. So that's nice. Now, obviously, if you do simulations, then you can make things quite fun quite easily. So here you see some Janus particles, and with Janus particles we mean an anisotropic particle in chemical identity in this particular case. So if we looked at the picture that we had before, we had a white sphere and a blue and a gray phase, the top picture. We can see that on the bottom bit here, well, we can basically clearly see that if we make that bit green, that maybe if green likes gray better than it likes blue, it should sit like this. Yeah. Now the thing is that if you play a movie of this, that not necessarily stands up anymore. So we've basically made a particle of which blue likes blue and gray likes gray. And if there's a weak preference, you can see on the left-hand side that particle tumbles. And sometimes the blue bit touches the gray phase, and sometimes the gray bit touches the blue phase. And that's not very favorable. Yeah? So this particle sometimes sits correctly, but sometimes inverts, and that's a very unfavorable energetic interaction. Whereas if there's a strong preference for blue with blue and gray with gray, you can see that the particle doesn't do this. It wobbles over the capillary wave, but it doesn't invert. So if people draw that Janus particles always just lie like that, with the face liking the face most, that's not always the case. So you have to imagine that these things are mobile and they can tumble, and as a result of that can end up in a position they do not like to be in.